in our discussion previously, we have defined what an equilibrium constant is. We have seen the different types of equilibria and how to calculate the equilibrium constant. Now, we want to look at the application of the equilibrium constant, and there are various applications that you can use the equilibrium constant. First is the qualitative interpretation of an equilibrium constant. Like what does it mean when you look at the magnitude of the equilibrium constant? What does it tell you about the equilibrium that exists? Does it favor the products or does it favor the reactants? Okay. And this one we saw previously in our discussion about the equilibrium constant. We saw how the magnitude tells you which side of the reaction is favored. Now, the other two applications of the equilibrium constant are predicting the direction of a reaction and calculating the equilibrium concentrations. Okay. So you have, when you're given a certain value of the equilibrium constant and for a given reaction, and then you have the initial reaction, then the initial concentrations. What equilibrium concentrations are going to be achieved in the end when equilibrium is established? So that is where the equilibrium constant finds utility. Okay. Firstly, we look at predicting the direction of a reaction. Okay. So you're given this example of a reaction here, a reaction of hydrogen gas and I2 gas to form hydrogen iodide. Okay. And you're told that this particular reaction, which is at equilibrium, the equilibrium constant is 54.3 at 430 degrees Celsius. So suppose that in the experiment, initially you have these concentrations or this number of moles of the species in this reaction. So you have 0.243 moles of hydrogen, 0.146 moles of iodine, and 1.98 moles of hydrogen iodide. These are the moles of these species placed in 1 liter container at 430 degrees Celsius. So what will be the direction of the reaction? Will there be a net reaction to form hydrogen and iodine or more hydrogen iodide? So in this reaction, notice in this setup here, all the species are introduced at certain concentrations at the start. Okay, so these, you can calculate the initial concentrations using the number of moles that you've been given here, because they are all contained in 1 liter, in a 1 liter container. So moles of hydrogen are going to be 0.243 moles per liter. This one is 0.146 moles per liter, and this one is 1.98 moles per liter. Okay, so looking at this reaction here, the equilibrium constant expression here will be written by concentration of hydrogen iodide squared divided by the concentration of hydrogen times the concentration of iodine. Okay. So this quotient or this ratio of these concentrations gives you the equilibrium constant, but only when you're considering the equilibrium concentrations. Okay. So we want to see, given these initial concentrations of the species, which direction will the reaction go as it moves towards achieving equilibrium? Okay. So first of all, we use this expression to calculate a quotient, the ratio of these concentrations. So we denote them with this. Notice that now here we have indicated the concentration. So concentration of hydrogen iodide naught. These naught here represent the initial concentration, because what we are going to get here is not the equilibrium constant Kc, but you're going to get a new quotient, okay, which is referred to as the reaction quotient, because you are considering a state which is not at equilibrium. So it is denoted as reaction quotient, that is QC. So we put in the values of the concentration of the species. Remember here you said you can use this per liter for hydrogen, these moles per liter for iodine, and these moles per liter for hydrogen iodide. So when you put those concentrations, we have 1.98 squared divide by 0.243 times 0.146. Okay, those are the initial concentrations. Now, when you calculate this, you get a value of 111 as the value of the quotient that we have calculated here. So this quotient is greater than Kc. Remember here we are told that the equilibrium constant for this reaction is 54.3 at 430 degrees Celsius. So the value I've gotten here is greater than the equilibrium constant. So this means that this system is not at equilibrium. So if it is not at equilibrium, it means the system will move towards achieving an equilibrium. So for you to predict the direction of a reaction as it moves towards equilibrium, you consider the value of QC. Is it less than Kc? Is it greater than Kc? Or is it equal to Kc? Okay, so those values are the ones that are going to help you now to predict the direction that the reaction will take. So here we consider three cases. We consider a case where QC is less than Kc. That is the quotient that we have talked about here. If it is less than Kc, it tells us something. Yeah? It tells us that the ratio of the initial concentrations of products to reactants is too small. So here, if the quotient that you're getting is less than Kc, it means that this product here of the concentrations of the reactants is larger than this square of the concentration of the product. Okay, so for you to be able to increase the magnitude of that value, you have to increase the numerator in this case. Okay, so to increase the numerator, the direction needs to move towards the at the side where you're producing more of this HI. Okay, so to reach equilibrium, reactants must be converted to products. Reactants in this case are hydrogen and iodine. The system proceeds from left to right. Okay, that is consuming the reactants, forming products so that it can reach equilibrium. So here, QC, when QC is less than KC, reactants are converted to products so as to bring this to a level where it is equal to KC as it moves towards equilibrium. So when QC is less than KC, reactants are converted to products. So that is the direction of the reaction. In this case, it's not the case because we have QC being greater than KC in this case. There's another case where you have QC. You can find that the initial QC, when you've put in the initial concentrations, the quotient you get, the reaction quotient QC, you can find it to be equal to KC. So what that means is that the initial concentrations are also equilibrium concentration. So the system is at equilibrium. So in that case, you're not going to have any net change in the reaction. It does not favor either side of that particular reaction. You can have a case where QC is greater than KC, which is the case for our reaction here. QC is greater than KC. So in that case, the ratio of initial concentrations of products to reactants is too large. Okay, when we consider an example here, since this is greater than KC, it means that you have more of HI initially. So for this particular system to move towards equilibrium, you need to reduce the amount of HI. So that means the reverse reaction, that is moving from the product to the reactants, is what will be favored. Moving from HI, converting into hydrogen and iodine. So that means the reaction moves from right to left. Okay. So to reach equilibrium, product, in this case it is HI, must be converted to reactants. This is H2 and I2. The system proceeds from right to left, converting products, forming reactants to reach equilibrium. So in this case, when QC is greater than KC, the direction of the reaction is from right to left. Okay, so this is how you would use the quotient, the reaction quotient, for you to predict the direction of the reaction. Okay. Now another application of the equilibrium constant is that you can use the value of the equilibrium constant and the initial concentrations for you to be able to find the equilibrium concentrations. So for example, here you have an initial concentration of A, for example. As it moves towards equilibrium, it is being used up and B is being formed. So it means there's a certain change. This one changes or reduces, and the concentration of this one, B, increases. Okay, so there's that change in concentration. And considering what happens for the reactant and the product, and having the value of the equilibrium constant, you can be able to now determine the equilibrium concentrations of A and B. So here we are saying that if the equilibrium constant for a particular reaction is known, the concentrations in the equilibrium mixture can be calculated from the initial concentrations. So in most cases, only the initial reactant concentrations are given. Of course, that's not always the case. You can have another case where you have all the species being present initially. So here, consider this reaction, A converting to B, and they are at equilibrium, and the Kc value is 24 at a certain temperature. A is initially present at 0.850 moles per liter. How do we calculate the concentrations of A and B at equilibrium? Okay. So considering that, we are saying that A is the reactant, and initially it is present at 0.850 molar. Okay. So this here represents the initial concentration of A. And B initially, there is no B present. So the initial concentration is 0 molar. Okay. Now, as it moves towards equilibrium, the concentration of A reduces or changes by negative X. So it reduces, we say, minus X. That's how it changes. And then the concentration of B changes by plus X. So notice here, we are saying minus X plus X because the mole ratio here is 1 is to 1. 1 mole of A produces 1 mole of B. So therefore, the changes are the same, minus X, and this one increases by plus X. So if we find the net change, then we are going to have the equilibrium concentrations. So the equilibrium concentration of A is going to be 0.850 minus X molar. And the concentration of B is going to be, so 0 plus X is going to be X molar. So the equilibrium constant expression for this is given by Kc equals to the concentration of A divided by the concentration of B divided by the concentration of A. So if we put in our values here for, that is the expression for equilibrium concentration of A and equilibrium concentration of B and the value of Kc, then we end up with this expression here. Kc was given as 24. So that means 24 equals to concentration of B at equilibrium, that is X, divided by the concentration of A at equilibrium, which is 0.850 minus X. Okay. So here we have just indicated that solving for X, we get that X equals to 0.816. This one you can easily work it out. You just multiply this both sides, and then this gives you, and then you combine the like terms with X on one side, then you can be able to find the value of X. Okay. So having found the value of X as this, then we can also be able to calculate the equilibrium concentrations, because we just put it into these expressions for the equilibrium concentration for A and B. So concentration of A is 0.850 minus X. So now we have the value of X. So putting it there, it's going to be equal to 0.034 molar. Okay. The concentration of B, that is the equilibrium concentration of B, is given as X from our calculation. So therefore, it's going to be equal to just the value of X, which is 0.816 molar. So this is how you would use the equilibrium constant now to determine the equilibrium concentrations once you know the initial concentrations of the species. Okay, let's look at another. So in summary, how do you do it? First of all, you express the equilibrium concentrations of all species in terms of the initial concentrations and a single unknown, that is X. Okay, which represents the change in concentration. Secondly, you write the equilibrium constant expression in terms of the equilibrium concentrations. So here, knowing the value of the equilibrium constant, you can solve for X. Okay. And once you have solved for X, then you can calculate the equilibrium concentrations of all the species in the given reaction. Okay. Let's look at another example here. A familiar reaction, that is a formation of HI from H2 and I2. So in this case, you have a mixture of the reactants. You have 0.5 moles of hydrogen and 0.5 moles of iodine placed in a 1 liter flask, stainless steel flask, at that temperature. So of course here you can calculate the concentration of hydrogen. It's going to be 0.5 moles divided by the volume in liters. So essentially the concentration of hydrogen is 0.5 molar, okay? Or 0.500 molar. Concentration of iodine is going to be this number of moles divided by the volume in liters. So this one you also get as 0.5 molar. Okay. Yes. Now these are the initial concentrations of these species. Calculate the concentration of hydrogen, iodine, and HI at equilibrium. So of course, this being the initial concentration, they would react to form HI until an equilibrium is established. At equilibrium, the three species will exist. So the question is, what are the concentrations at equilibrium? Given that Kc, the value of Kc is 54.3 at this temperature. So we move the similar way that we looked at the other example. Hydrogen plus iodine gives us hydrogen iodide. Please notice the mole ratio. Here you have 1 mole of this and 1 mole of this, giving us 2 moles of HI. So initially, we have 0.500 molar of H2 and 0.500 molar of I2. But we don't have any HI. So therefore we have 0.00 molar of HI. That is the initial concentration of the species. As it moves towards equilibrium, there's a certain change that the concentrations undergo. So if we say the concentration of H2 changes by, it reduces, because it is reacting to produce HI. So therefore we say if it changes by minus X from the mole ratio, iodine will also decrease by the same amount, that is minus X molar as well. Now, HI will, because of the mole ratio here, it will increase by 2X. These ones are reducing by X. This one will increase by 2X molar. Okay, so if we look at the net change, the equilibrium concentrations can be given by 0.5 minus X. So this is the equilibrium concentration of H2. And iodine decreases by X. So it is 0.5 minus X molar as the equilibrium concentration of I2. And the concentration of HI, it increases by 2X molar. Okay, so those are the equilibrium concentrations of these species. So the equilibrium constant here is given by this expression here, that Kc equals to Hi squared divided by concentration of H2 times the concentration of I2. These are the equilibrium concentrations. So if we substitute the equilibrium concentrations that we have found here into our expression here, it becomes, we know that Kc equals to 54.3. This equals to concentration of Hi at equilibrium squared, which is 2X squared, divided by concentration of H2 at equilibrium, which is 0.500 minus X, and the concentration of iodine at equilibrium, which is 0.500 minus X. Now you notice something here. The numerator and the denominator are both squares of a particular value. So this one is a square of 2X, and the denominator here is the square of 0.5 minus X. So that means we can simplify, this simplifies our quest to find X. We can just find the square roots of both sides. Okay, so that eventually here we get the square root of 54.3 being equal to 2X divided by 0.5 minus X. So it simplifies our calculation. So if we do that, I think this is 7.37, okay, equals to 2X divided by 0.5 minus X. So again here, if you take time to calculate this, you should find that the value of X is 0.393 molar. So now, having that, then we can find the equilibrium concentrations. Equilibrium concentration of H2 was going to be 0.5 minus X. So X the value has been found in this case. So the difference there gives you 0.107 molar as the equilibrium concentration of hydrogen. For iodine, it was also 0.5 minus X. So since you have the value of X, now you also get the equilibrium concentration of iodine as 0.107 molar. Concentration of hydrogen iodide was 2X. So 2 times the value of X, you get the concentration of hydrogen iodide as the being 0.786 molar. Okay, so these are simple ways of finding X. Here you end up with an expression that you can easily find the value of X. But there are certain cases where you end up with quadratic expressions. So where you end up with quadratic expressions, you might have to solve those quadratic expressions to find the value of X. So you need to remind yourself on how to solve quadratic equations in case as you are looking for the value of X, you end up with a quadratic expression. Okay. So I'd like to stop there for now. We'll continue and look at how you can, how the utility of the equilibrium constant, how you can be able to look at the effects if you change the conditions of a reaction. Yeah. How does it affect the equilibrium? If you change the, for example, the temperature, if you change the pressure, or if you add a catalyst, what happens? So we look at that in our next recording that I'm going to be sending.